Hello, welcome to the video on Introduction to Subsets. Here are some definitions and symbols you should recognize. Subset, a set whose members are also all members of another set. Here's a more formal definition. Given two sets A and B, set A is a subset of set B if every element of set A is also an element of set B. Here are some symbols that are used for subsets. A is a subset of B, or A is not a subset of B. So let's take a look at some examples. Here is our set M. Our set M is all of the dogs recognized by the AKC whose names begin with the letter M: the Maltese, the Manchester Terrier, the Mastiff, the Miniature Bull Terrier, the Miniature Pinscher, and the Miniature Schnauzer. And our set N is the Miniature Bull Terrier, the Miniature Pinscher, and the Miniature Schnauzer. N is a subset of M because all of the elements of the set N are also members of set M. We can write this as N is a subset of M, using the symbol which looks like a sideways U with an underline. Here's our set M. Once again, our set M is a set of all the dogs whose names begin with the letter M that are recognized by the AKC: Maltese, Manchester Terrier, Mastiff, Miniature Bull Terrier, Miniature Pinscher, Miniature Schnauzer. Our set P is a Pug and a Miniature Bull Terrier. Set P is not a subset of set M because one of the elements of P, that is the Pug, is not a member of the original set M. So remember, to be a subset, all members of the subset have to be members of the original set. So in this case, since the Pug is not, this set P cannot be a subset. We write this as P is not a subset of M by putting a slash through the symbol, which looks like a U on its side with an underline. So you probably remember from inequalities that the symbol that looks like this, sideways V with an underline, means is less than or equal to, meaning that both of the following statements are true. 3 with that symbol is read, 3 is less than or equal to 5. And this is true because 3 is, in fact, less than 5. 5 is less than or equal to 5 is true because 5 is equal to 5. Although it is not less than, it is equal, so it's true. And just like the 3 is less than or equal to 5 is not equal to 5, but the statement is true because it's less than 5. And this would be similar for numbers using the greater than or the greater than equal to symbol as well. So that underline beneath the symbol is important. The underline of the symbol means that every set is a subset of itself. Now, this will make more sense in a bit, but just accept that for now, that every set is a subset of itself. So if set A has elements 1, 2, 3, 4, and 5, and set B has elements 1, 2, 3, 4, and 5, we could say A is a subset of B because sets A and B are identical. We could also say A is a subset of A because A is identical to itself. And think of this as similar to 5 is less than or equal to 5. When two sets are equal, they are considered subsets. Now, there is such thing as a proper subset. A proper subset is a set whose members are all members of another set, just like a subset, but whose members are not exactly equal. So in this case, when we're talking about proper subsets, we exclude the original set itself. A more formal definition: set A is a proper subset of set B if set A is a subset of set B and sets A and B are not equal. So excluding the case where the two sets are exactly equal, every other subset is called a proper subset. The symbol for a proper subset, well, just like the missing underline indicates that sets cannot be equal, just like less than and greater than mean the numbers can only be less than or greater than and not equal. The same thing is true for the symbol about proper subset. It's just the shape that looks like a U on its side, but there's no underline. And this is read, A is a proper subset of B. If we see this, we know that A and B are not exactly the same. Now, with inequality notation, we can write both 3 is less than 5 and 3 is less than or equal to 5, and both are true and both are acceptable. For the set of vowels, or V equals A, E, I, O, U, and set W equals I, O, U, we can write W is a subset of V, and W is a proper subset of V. Now, the reason we can say it's a proper subset is that it's not exactly equal to V. It just has 3 elements I, O, U, which are all elements of set V, A, E, I, O, U, but it doesn't contain all the elements of V. That makes it a proper subset. Once again, these are read. Set W is a subset of set V, and set W is a proper subset of set V. That just means that it's not exactly equal to the set. Both are true and both are acceptable, just like 3 is less than 5 is acceptable and 3 is less than or equal to 5 is acceptable. Now we want to go about finding all the subsets of a set. And remember, earlier we stated that every set is a subset of itself. Now, not a proper subset, but just a regular subset. And we did say we would come back to that, so now we're back to that. And so let's say we have this set I, which is equal to 5 ice cream flavors: strawberry cheesecake, chocolate chip cookie dough, cheesecake brownie, cherry Garcia, and butter pecan. Then there is a subset that we'll call J, which is J equals strawberry shortcake, chocolate chip cookie dough, cheesecake brownie, cherry Garcia, and butter pecan. So we can say that J is a subset of I. But remember, it's not a proper subset any more than 5 is less than 5. Remember, 5 is less than or equal to 5, but you can't say 5 is less than 5. That's just not true. So you must use the symbol for subset and not proper subset. Remember, if two sets are equal, one is not a proper subset of the other, but it is a subset of the other. Now, here's another thing. The empty set is also a subset of all sets. So if we've got a set I, which is equal to 5 flavors of ice cream, we could say that the empty set is a subset of this set I, of these 5 ice cream flavors, or that the null set is a subset of this set I, of the 5 ice cream flavors. And that's because the empty set, which is the same as the null set, is a subset of every single set. It can be counted as a subset of any set, that is the empty set or the null set. We can even say that the empty set is a proper subset of this set I of the 5 flavors, or that the null set is a proper subset of this set I, the 5 flavors, because it's certainly not identical to the original set I. Now, we can say that the empty set is a subset of the null set, or the null set is a subset of the empty set, but we can't say that they are proper subsets of each other because they're equal to each other. So remember, proper subsets cannot be identical. Any proper subset has to have at least one element less than the original set in order to be a proper subset, because they cannot be identical. It has to have less elements. Now it's going to start to make a little bit more sense, and you'll understand a little bit more about why we have to do this. So sticking with our original set, here's a great problem to have regarding these 5 flavors of ice cream. Let's say you've gone into an ice cream shop where you've been told by the shop owner that for free you can have any combination of the ice cream flavors you'd like to have under 2 conditions. One is you cannot have more than 1 scoop of each flavor. So you're limited to 1 scoop of each flavor. And 2, before you get the free ice cream, you have to tell the shop owner how many different ways it would be possible for you to request the ice cream. Now, at first, this may seem very simple, to just count these out. But maybe it's just not as simple as it first seems. So once again, we're going to find all the subsets of this set of these 5 flavors of ice cream. And hopefully, here's where it will really start to make sense. One of your responses might be something like, "Thanks, but no thanks. I'm lactose intolerant." So in other words, you don't have any of the ice cream. That's an empty set, and that's one of your choices. If you were offered this ice cream and the ability to choose it any way you wanted to, as long as you didn't choose the same flavor twice, you could certainly say, "No thanks, I'm going to decline." And that would be the empty set, because we've not chosen any members of the set. It's an empty set. And also, after a bit of thinking, you could say, well, there are a total of 32 different ways that I could choose this ice cream. And then the real fun begins when you start to find 32 different combinations. So remember, we've got to figure out, how do we get from those 5 original elements in that set to 32 subsets of the set? So to make it simpler, we're going to convert over to real roster form. I've used pictures just to make it a little more interesting, but let's convert over to roster form, and that's where you list out names. And so our set I for ice cream is going to be SC for strawberry cheesecake, CD for the chocolate chip cookie dough, CB for the cheesecake brownie, CG for cherry Garcia, and BP for butter pecan. So our original set I consists of 5 elements, these 5 flavors, and we must remember that we're not allowed to have more than 1 scoop of each of these flavors. So here is a table that shows you the total of all the ways you could pick this ice cream. Notice in the first column it says total 32. Well, as we read down the columns, we see, first of all, we could choose, like my first example, is just to choose nothing. Well, that's a choice, and that is, no thanks, I'm not going to have any ice cream. That's considered a choice. And then you could just choose 1 scoop of each of the ice creams. And so I've written the sets with just 1 element in each set. The first one, just the strawberry cheesecake, and then the chocolate chip cookie dough, and then the cheesecake brownie, and then the cherry Garcia, and then the butter pecan. So I'm reading down this way, and you can see, if you count these up, there are 5 ways that you could choose to have a single scoop, and that is to have 1 scoop of each of the flavors. Then it gets a little harder when you get up to 2 scoops. So you have to start matching up the first one with each of the others. And so that's why you'll see strawberry cheesecake, chocolate chip cookie dough, and then strawberry cheesecake, chocolate brownie, and then strawberry cheesecake with cherry Garcia, and strawberry cheesecake with butter pecan. And if you continue in this way of selecting 2 flavors, 1 scoop of each flavor, you would end up with 10 different choices, and these are all completely distinct. Now, if you were to pick chocolate chip cookie dough and strawberry cheesecake, well, that would be the same as strawberry cheesecake and chocolate chip cookie dough. It doesn't matter what order you choose the scoops in, it still would be the same ice cream. So you don't see those appearing twice. There are 10 ways to pick 2 of them. And you can look at those and verify that those are just 10 ways. And when you get to 3 scoops, there are also 10 ways to choose the 3 scoops. I'll just read a few of the examples. Strawberry cheesecake, chocolate chip cookie dough, and cheesecake brownie. Or how about cheesecake brownie, cherry Garcia, and butter pecan? Let's see. Cheesecake brownie, cherry Garcia, butter pecan. That's the last one I've listed. So all of these are distinct different ways that we could choose a subset of the original 5 flavors, 1 scoop per flavor, but getting 3 total scoops. Then we can go on to 4 scoops, and you'll see that there are 5 ways for that. And then, of course, the ultimate would be, you know what, I'll have 1 scoop of each. That's actually the original set. So there's a total of 32 subsets of this original set, as long as we include the choice to have nothing at all, the empty set, and the choice to have 1 of each, which is the original set. Now, I know what you're thinking. There's got to be a better way to count these, because what if you had, you know, a lot more flavors, like 6 flavors or 10 flavors, or maybe even 32 flavors, like that famous other ice cream place with 32 flavors. The number of sets can get really astronomically high. So here's the shortcut. The number of subsets of a set B with n elements is a very simple power. 2, the base 2, to the nth power. And it's always base 2. 2 raised to n, where n is the number of elements. So it's a pretty easy formula for finding the total number of subsets. Now, the number of proper subsets of a set B with n elements is 2 to the n minus 1, because in order to be a proper subset, it can't be the full original set. So if the ice cream shop owner had said, pick as many ways as you want to, but you can't have all 5. The most you can have is 4. And so that would exclude the original set, and all the rest of those sets would be proper subsets because they're not equal to the original set. 5 elements, so the number of subsets is 2 to the 5th, which is 32. The same number we got when I listed 1 by 1 by 1, the number of sets with 0 elements, the number of sets with 1 element, the number of sets with 2, with 3, with 4, and with 5. So unless you're specifically asked to do it, you don't have to list out all the sets, because all you have to do for every problem where you know the number of elements in a set is take the number 2 and raise it to the power n, where n is the number of elements in the set. And of course, the proper subsets for this set of 5 is 31, because you subtract 1 from the total number of sets, because you're subtracting away the original set, and you would have 31 in this case. So imagine if you were at a certain ice cream shop where they have, say, those 32 flavors. Well, your choices would be 2 to the 32, which is 4,294,967,296 distinct choices. That's all the subsets of that set of 32 elements of different flavors. Or if you want to look at the proper subsets, in other words, you're not going to get all 32 scoops. It would be that number minus 1. So 4,294,967,296 minus 1, or 4,294,967,295 choices, because you do not count the original set of all elements. So here are a couple of examples, and we'll use the shortcuts this time, but sometimes you might want to write out the sets just to prove to yourself that it actually works. So there are 24 students in an online class. If they have to work in groups on a project and the group size can range from 1 to 24 and no student can be in 2 groups, how many different groups are possible? Now in this case, we're going to say you can't have a group of 0 students. In other words, you have to have at least 1 student. And so in this case, we're not going to count the empty set, because a group of no students would be the empty set. So we've got 24 students in the class. So 2 to the 24th would be 16,777,216. But that would be all of the sets. So if we're going to exclude the empty set, we would have to say our answer is 16,777,215 ways that these 24 students could group up, assuming some individuals could group by themselves, and then there could be groups of size 2 and 3 and 4 and 5 and 6 and 7 and 8, all the way up to 24. That is 16,777,215 different ways, excluding the empty set. That's a lot of ways, and only 24 students. So as I said before, the numbers can get astronomically high on this kind of thing. Example 2. An ice cream shop has 16 toppings that can be placed on top of a sundae. If a shopper gets a cup of vanilla ice cream, how many different ways can this be served? So it's kind of like the scoops, but this time we've got a cup of vanilla ice cream, we've got all these different toppings, and we've got 16 different toppings. Well, if we've got 16 members or elements in our set, and we want to know all of the subsets of the set, all the possible different ways we could choose from that set of the original 16, the answer would be 2 to the power 16, because there's 16 elements. And that turns out to be 65,536. Now, we're not asked for the proper subsets here. It is possible that the shopper could choose all, and it's also possible that the shopper could choose the null set, and that is to have no topping on the cup of vanilla ice cream. So since every set is included, not just proper, it's our base of 2 raised to our number of elements in our set, 16, which is 65,536 different ways that this cup of vanilla ice cream could be served.